We want to find out the limit of the integral from 0 to half pi of sine to the power of n of x dx as n approaches infinity. And we're going to be using this lemma, and this lemma. So we can rewrite this integral into 0 all the way up to half pi minus 1 over cubic root of n of sine of to the power of n of x dx plus the integral from half pi minus 1 over cubic root of n all the way up to half pi of sine to the power of n of x dx. Now we already know this integral is larger than or equal to 0 because sine of x is larger than or equal to 0 over this interval. If we raise it to the power n, still larger than or equal to 0, no problem. Now we want to show that each of these integrals approach to 0. Then when you add them together, still approach 0. Therefore, using squeeze theorem, we can easily prove that the limit approaches 0. So let's first look at this integral. All right, because I know that sine x as well as sine to the power of nx is an increasing function over this interval. Right? N is some positive integer. Right, so therefore I can replace x with the right end edge and make it larger. So this is less than or equal to sine or to the power n of this constant. So this becomes constant. Take the constant out of the integral to the front, times the length of the interval. That is half pi minus this quantity. But then I can further loosen the inequality by replacing the length with just half pi. Half pi is larger than this quantity. So this is loosened to half pi times the sine of to the power n of half pi minus 1 over cubic root of n. This is my first integral after loosening. Plus, how can I lose this inequality? Well, replacing sine of x with just 1. Right? So therefore it becomes larger. So this whole thing becomes 1 times the length of this interval. The length of this interval is simply just 1 over cubic root of n. So keep this in mind. This quantity approaches 0, obviously, as n approaches infinity. Now our only job is to find out this limit and show that this limit is 0. The constant is fine, times infinity. We just have to show this quantity approaches 0. Now let's take the logarithm of this quantity. So the log of sine to the power of n of half pi minus 1 over cubic root of n, using logarithm rule, take the power to front, equals n times log of sine of half pi minus 1 over cubic root of n. Now, that is equal to n times log of cosine of 1 over cubic root of n. That is using trig identity. Sine of half pi minus something equals cos of that something. So remember, as n approaches infinity, this quantity approaches 0. Therefore, we can utilize the Taylor expansion, Taylor series near the point 0. Cos x can be written like this. So x is my 1 over cubic root of n. This is my x. So this is equal to n times log of bracket 1 minus half of x squared. X n to the power n to the power 1/3, since it's at the bottom, so therefore it's n to the power of minus third. So times, then square it. So times n to the power of minus 2/3. Right? Then plus little omicron of, again, so what's the meaning of little omicron? For example, if we're given some quantity little o of some f of x, some function of x, basically what that means is that if we divide it by the quantity inside, that quantity approaches 0. That's the meaning of little omicron. As x approaches some constant, x naught. If f of x also approaches 0, so what does that mean? That means some quantity divided by an infinitely small amount still approaches 0. That means the quantity on the top approaches 0 faster than the quantity at the bottom, if the bottom approaches 0. But f of x does not always approach 0. Sometimes it's approaching some constant. Sometimes it's approaching to some, don't have a limit, whatever. Maybe infinitely large. So that's what it means. So little omicron of x cubed. The reason I write x cubed is because we could have written x squared, because we're ending with x squared. So, but I'm writing x cubed because I assume that the following term is just 0. It's because the third degree of derivative at point 0 is already 0. Therefore, I assume there is a third term here. It just automatically becomes 0. Therefore, I just write x cubed. So omicron of x cubed. So this cancels out, becomes 1 over n. So omicron of 1 over n. So basically, as n approaches infinity, 1 over n approaches 0. So that means little omicron of 1 over n, meaning this quantity approaches 0 faster than 1 over n. Keep this in mind. So we have this. And remember, the limit of log of 1 plus x over x approaches 1 as x approaches 0. Therefore, what is my x? 1 plus. So this is my x. This is 1. This is x. Does x approach 0? So this, as n approaches 0, 1 over n approaches 0, omicron of this, so divided by, so even if it's divided by over, it still approaches 0. So this one is fine, approaches 0 as an approach. So this one is n to the power negative 2/3. So it's 1 over n to the power of 2/3. So this quantity obviously also approaches 0. So that is simply equal to n times, replacing with x, so times bracket minus half times n to the power of minus 2/3 plus little o of 1 over n. Okay, so we can just simply multiply everything out. That becomes n to negative half times n to the power of 1 minus 2/3. That is 1/3 plus n times little, so it becomes omicron, little o of 1. We can this legitimate. Just multiply this inside here. This is easily verifiable. Now, so keep this in mind. This quantity is already approaching 0. So don't worry about this one. Just focus on this quantity. As n approaches infinity, n to the power 1/3. As long as the power is positive, then this quantity approaches positive infinity. But we have a minus constant times that. So this whole quantity approaches negatively infinity. Negative infinity. Therefore, since the log value approaches negative infinity, that means whatever that's inside log should approach 0. Right? So this should approach 0. So this quantity should approach 0, right? So this whole quantity should also approach 0. We're done. So 0 plus 0, right? 2 infinitely small plus together, still infinitely small, right? So 0, 0 squeezed, right? This limit is really 0. And we, in fact, we don't have to use square root of a cubic root of n, as long as we have n to the power of alpha. N to the power of alpha. So 1 over n to the power of alpha, as long as alpha is larger than 0 and strictly less than half, it'll work. Not just for this, but as long as alpha is in this restriction, it always works. Here's how. So imagine if we have n to the power 1 over n to the power alpha, then that becomes alpha minus alpha. That becomes n to the power of minus 2 alpha. So times n to the power of, so if it were alpha, then we would have something like this. Minus half times n to the power of 1 minus 2 alpha. Plus little o of, so this becomes n to the n to the alpha, n to the minus alpha, n to the minus 3 alpha, n to the power of 1 minus 3 alpha. So that means this quantity, if divided by the quantity inside, approaches 0. Now, so the little omicron of n to the power of 1 minus 3 alpha divided by n to the power of 1 minus 3 alpha approaches 0. As n approaches infinity. So that means when n is large enough, this quantity is small enough. So that means at some point, this quantity should be small enough, less than or equal to 1. Right? This is achievable, of course. Then multiply this over here, then we have little omicron of n to the power of 1 minus 3 alpha is less than or equal to n to the power of 1 minus 3 alpha. Right, so this quantity, I can claim that is less than or equal to n to the power of 1 minus 3 alpha. And let's compare the, because eventually I want to show that this whole quantity approaches negative infinity. So in other words, I already know this quantity approaches, because alpha, like I said, is less than half and larger than 0. Therefore, 1 minus 2 alpha is strictly larger than 0. Right? In that case, of course, this quantity easily approaches negative infinity. And all I need to show now is I want to show that this quantity does not affect the tendency of this negative infinity. Why? Because let's compare the powers. Right? Which power is larger? 1 minus 2 alpha or 1 minus 3 alpha? Right, here the power is 1 minus only twice of alpha. Alpha is positive. Here I'm minus something bigger, minus 3 times of alpha. Of course, this power should be smaller than that power. So that means even though even if this quantity approaches infinity, it should not affect this quantity. Why? Because the power of this n is larger than this power, right? So they both maybe approach infinity. But this quantity approaches infinity slower than this quantity, right? So overall, the overall effect should still be negative infinity, right? If the power is positive, but even though power is positive, but this power is still smaller than that power, right? But if the power is somehow negative, then we have can be written as 1 over n to the power of some positive power. Then that is easily approaching 0. Of course, cannot affect the overall tendency of this negative infinity either. So in either cases, we can easily show that this the overall result of the log value should approach negative infinity. Therefore, the inside quantity should approach 0, as long as alpha is within this restriction, right? 1/4, 1/5, whatever. Strictly larger than 0, strictly less than half.